Alright guys, so what I'm going to try to do with this video is I'm going to try to do a step-by-step walkthrough of the midterm review final. The one I'm using appears slightly different from the one you have, but most of it's still the same. There's one or two things I had to cut. COVID has made me have to dwindle down a little bit of the information that we had to do this year. So, yep, that's that. All right, so first, what we're going to do is we're going to work on these first few problems here. So, don't fight me. Okay, cool. All right, so we're going to work on these first few conversion problems. I'll give you a second, pause the video, you can make sure you got the answers correct, and then I'm going to go over both of the density problems and the conversion problems. So, switch over to the old PowerPoint. All right, so let's look at these. First and foremost, remember, whatever we start with, we have to put at the bottom. Okay, we have to get our units to cancel. And then remember, we put the 1 with the larger unit. Liters are larger than milliliters. They are 1,000 times larger. So this comes out to 0.0598 milliliters. Okay, so got that going. That's a nice, easy one to start with. And now we'll move into a little bit more difficult one. Now, with this one, remember, this is a very large transfer from kilograms to milligrams. If we remember our King Henry died by, which is our base unit of meters, liters, and grams, drinking chocolate and milk, all right, we got a pretty far way to go. So I find it best for students to take a pit stop at the base unit. In this case, it'll be grams. So we'll put grams here, kilograms right here. Kilograms cancel. Kilograms are a larger unit. They're 1,000 times larger than grams. So now we're in the unit of grams, but we need to get to milligrams. Grams on the bottom. Grams cancel. Grams is a larger unit. It is 1,000 times larger. Okay? So 4.1 times 1,000 times 1,000 gives us 4,100,000 milligrams. Okay? All right. Kind of the same thing, just going from a small unit to a large unit. And this one went from kilograms, which is a fairly large unit, to a fairly small unit. Here we're going to go from a fairly small to a fairly large. Okay? So, centimeters goes on the bottom. This time our base unit is meters. Okay? Meters gets the 1. There's 100 centimeters in every meter. Okay? So now we got to get rid of meters. All right? Kilogram is larger, or kilometer, sorry, is larger, and it's 1,000 times larger than meters. So meters. All right, units cancel. We're left with kilometers. So it's 14.3 divided by 100 divided by 1,000. 14.3 divided by 100 divided by 1,000. My calculator work today. 0.000143 kilometers. All right. A little bit easier one. Meters to centimeters. So meters are larger, 100 times larger. So we should end up with 27 centimeters. Okay? All right. 2 more. All right, so we got kiloliters, or liters to kiloliters. Once again, liters goes on the bottom to get rid of that. Kiloliters is larger. It is 1,000 times larger. So 18.9 divided by 1,000 equals 0.10 kiloliters. All right, last but not least, we're going from grams to milligrams. Grams on the bottom, grams get the 1,000. So it should be nothing. 6500 milligrams. Right? So we got 6,500 milligrams. That is our unit conversions from Unit 1. All right. Also in Unit 1, we had density. Remember, and this will be on your test, density equals mass divided by volume. Okay? So a very straightforward one to start out with. At 45.57 grams, I have 14.7 milliliters. All right, so 45.57 divided by 14.7 equals 3.1 grams per milliliter. Make sure you got your unit on there, guys. If you don't have your unit, it's always going to be -1. All right, so the next one, you got two options. I think plug and chug is probably the best for most people, but you can also rearrange the equation. So if here's my equation, but in this case, I'm going to need mass by itself. So to get mass by itself, multiply both sides by V, you get V times D equals mass. Okay? So then that's how you can rearrange the equation. Just plug it in, you get your mass. And now I'm going to show it with kind of plug and chugs, as we used to call it. Grams per milliliter equals M, we're looking for mass, and 11.5 milliliters. So once again, we got, like I said, multiply, get it out of the bottom, cancels, left with mass. So multiply this by 11.5, all right? 11.5 times 0.920 equals 10.58. Sorry, I forgot my little unit. Milliliters cancel. Left with grams, so our unit is grams. All right. The only other one I can ask you, or only other way, it's kind of like we did in lab with the lab practical. So I'm going to walk through this and we'll talk about how we pick out the data we need. The mass of a graduated cylinder is this. The mass of the graduated cylinder with the rock is that. Okay. So what we're going to do to find our mass of our rock will be 58.9 is our final mass from our initial mass. Okay. And that should give us 0 to 4 to 24 grams, right? Yep. All right, so we got our mass. Now we need our volume, okay? Before adding the rock, the volume level was 20.87. After we added the rock, it was 24.87. So once again, take our volume final, subtract it from the initial volume. Like how I made this easy for myself. All right, so here are two numbers that we're going to need. Okay, so mass, once again, divided by volume. (24) divided by 4. Density equals 6. Whoops. 4 milliliters, not 4 grams there, sorry. Grams per milliliter. So those are our potential for our unit conversions and volume, or density, sorry. All right, so let's get back to, so we got all those done. All right, so let's talk a little bit about some of these others. All right, so down just a little bit, that way it fits. All right, matter. Matter is anything that has a volume and a mass, okay? So, when we talked about electrons, they make up matter even though their mass is ridiculously light, okay? They do have a volume, they do take up space, and they do have a mass. It doesn't matter how light the volume is per se, it just has to have a mass or a volume, period. Now, a pure substance is a sample of matter that has a defined physical and chemical properties. Okay, and really you can't break it down like you don't have, you have one compound can be a pure substance, but multiple compounds are going to be a mixture, which we'll talk about in a little bit. Okay, so the two examples for a pure substance are elements. I just wrote over that thing, and compounds. I'm doing a horrible job of this. I'm bored today. All right, so an element cannot be broken down into any smaller thing that has the function and has the properties of an element. So I can't break sodium down anymore and still have all the properties of sodium. I can't break oxygen down. I can break oxygen gas like O2 into just two pieces of oxygen, but they still retain all the properties of oxygen. Okay. Now with a compound, it is made up of two or more elements. Okay, in this case we got we got water, we got the hydrogen, which are the green, or the whites, and the reds, which are the oxygen. Okay, so they're bonded together in some way, shape, form, or fashion. You have two examples. You got covalent and ionic bonding here, but they're bound together by a chemical bond of some kind. Okay. Now, when we switch over, okay, we have a mixture. A mixture is a combination of two or more of these guys. Okay. So two or more pure substances that are not chemically combined. Keyword not chemically combined. I can separate them if I really, really need to. All right. Homogeneous mixture is something that is evenly distributed throughout. Like, so we got like salt water here. Okay. I could eventually boil off the water if I needed to, but by and large, they're good. They're together. They're not chemically bound together. They're just together. We can't really see all the little speckles of salt in there anymore. All right. Another one, on the other hand, would be heterogeneous mixture. Okay. These are not evenly distributed. Okay, we would be able to see clear defined layers of this. Okay, so we kind of drew it with salt and water here, but you can see how there's a clear divide between this side and this side. Okay, we did it in class where we had the little beaker, water. All right, the oil sitting on top of the water. Even if we shake it all up, it becomes like a hot mess. It'll always settle back to a mixture. Whoops, forgot. It'll always settle back to our mixture of water sitting on top, oil sitting on top, and water sitting on bottom. Okay, so they will eventually go back to where they came from. All right, page 2. That's all this good stuff. All right. So, I kind of put words over these models. You know, you can put it on the back, you can put it on the side. The first one is the atomic model. is the first one that we really have, the first model we talked about, is the billiard ball model. Shows that atoms are ball-like structures. The concept of nuclei and all that, electrons, things like that, are still to be found. So he just knows it as just more or less a ball. Okay. Then we get to J.J. Thomson with the cathode ray experiment. He finds that there are just a bunch of electrons in there. Now, essentially in your picture, you have what they call the plum pudding model, which is negatively charged particles with enough positive charge to help separate them. That way they don't essentially repel each other. Right? And then last but not least, we have Rutherford with the gold foil experiment. The gold foil experiment, we shot alpha particles at a thin piece of gold foil. The thought was that they were all, here's our thin piece of foil, here's our detector. All right, the thought is they were all just going to fly right through. However, most of them did fly right through, but some of them pinged back and pinged to the side. So that leads us to the idea that we have a nucleus, which with a positive charge, and then like the electrons kind of flying around the outside. We talked a little bit about Niels Bohr as well with the solar system model, where we realized that they were on different shells or different levels. All right, so that's kind of all you need to know from the atomic model, the theory of how we got to what we know as the atomic model. All right, so the current model that we have now, we can see it right here. All right. So we got our parts. We got our electrons, we got our protons, and we got our neutrons. Electrons are located on the outside of the nucleus in the electron cloud. The charge is negative and their mass is 0. And remember, mass is done in AMUs, or atomic mass units. Protons, they are in the nucleus. They have a plus charge, and they have a atomic mass of 1. Neutrons are in the nucleus as well. All right, they have no charge. All right, and they have a mass of 1. Okay, when we change our neutrons, we start changing our atomic mass. Protons never change. Neutrons can change. We talked about isotopes, and we'll talk a little bit more about them in just a second. All right. All right, so top part, atomic number. This is also and always the number of protons, okay? So make sure you remember that. It's always an easy answer, okay? You got your atomic symbol, and then you got your atomic mass. And remember, it is protons plus neutrons that make up our mass, okay? Now, isotopes. Isotopes, it is a change in the number of neutrons. It does not change the charge, because the charge of a neutron is what, once again? It is 0, okay, or no charge whatsoever, however you want to look at it. So, example would be boron 10. If you look at the periodic table, boron actually has a, on the periodic tables that we gave, the rounded ones, it has a mass of 11, okay? So we're telling you boron 10, so something's up with this. It's not the normal periodic table boron. All right, ions. This is a change in electrons. They can be either positive or negative. An example here is in a green, perhaps not the best color for that part. Okay, we can be, like I said, positive or negative. Sodium and another example would be chlorine. Sodium is positive. I think there's a mistake on the answer key. Chlorine is negative. All right. So let's fill in our chart. Now, I went on and filled this in. It was just easier to do it that way. Expect and try to have me try to write in all these, but I'm going to walk you through how we got to our answers, okay? So, on the review, you were given, for this first one, you were told that it was neutral. You were told that the neutrons were 8. The mass was 16, okay? So what I can do is I take my mass minus my neutrons. That's going to give me 8, which is my protons. Once I have my protons, I know exactly what element it's going to be. It's going to be oxygen. Because remember, the atomic number and the number of protons are the exact same. So our symbol is oxygen. It is neutral, so that means protons and electrons are going to be even. Once again, once I know the number of protons, these two numbers are always the same. All right? Protons and atomic number are always the same, so that's a pretty easy one to do. This one, I tell you the number of protons, and I gave you the charge, and that was it. Okay? That's enough, because protons tell us that it is silver and Ag. Protons, remember, always the atomic number, so I just look for element 47. If the protons are 47, the atomic number is always 47. Okay. We can do electrons next. I'm telling you it's +1. Now remember, electrons are negative, so if it's +1, it's lost an electron. So it'll be 47 minus 1. If you want to look at it like that, it'll be 46. And then last but not least, we take atomic mass, subtract neutrons, all right? Oh, sorry. I'm doing neutrons, my bad. So we take mass, subtract the number of protons, all right? And that'll give us 61, okay, for neutrons. All right, boron. I gave you all this, told you it was neutral, all right? So I look on the periodic table, find boron. I see that its atomic number is 5. That automatically means that my protons are 5. This 10 tells me the mass, so we can put 10, okay? I'm telling you it's neutral, so that means it's going to have the same protons and electrons, so make that 5. And then 10 minus protons, which is 5, gives us 5. All right, nitrogen, anion. Remember, anion means it's going to be negative, all right? And I'll tell you that with a -3 there, okay? So I know it's nitrogen. Won't be able to define the atomic number, which is 7, which means my protons are 7. I didn't give you the mass, so you're just going to have to use the mass off the periodic table, which would be 14, okay? 14 minus 7 gives us 7. Now, electrons, I'm telling you there are 3 extra electrons here. All right, well, once again, electrons, negative. Okay, so 7 plus 3 is going to give us 10. All right, last but not least, fluorine. Number of protons, give you this, and this. Well, if protons are 9, the atomic number is automatically 9. I have neutrons, and I have protons. Those two added up give me 19, which is our atomic mass. Once again, I'm telling you that there is -1, which means we have an extra electron. Ones are negative. All right, so that gives us 9 plus 1 is 10. All right, let's look at chemical and physical changes. All right, physical changes and chemical changes. So physical property is a characteristic of a substance that we can see without changing its identity. So hear, smell, taste. We're doing chemistry right now, so we're really not really tasting anything, but you get the idea. All right, touch and hear. Okay, these are our senses that we would use to find physical properties. So examples: density, color, Rippability, all these other kind of things would be luster, shine, in that lab that we did, okay? So these would be all examples of a physical property. A physical change is just a change to the form, but it does not change the identity. Keyword does not change the identity of it. If I were to go out and back chopping wood, all right, I wouldn't change the wood, I would just change what it looked like, all right? If I ripped a paper, which I did in class, I didn't change it into something new. I didn't make it new paper, all right? I just changed what it looked like. So some examples, ripping, chopping, grinding, crushing, right? All those things are examples of physical changes. Now when we get into chemical changes, it's a little different. All right, chemical properties. These are properties that are characterized, that give us characteristics of what the chemical changes that it could go through. So example, flammable, reacts with acid, reacts with base, all those other kind of things would be examples of chemical properties. Now, chemical change is where we change into something new, all right? So hydrogen gas, oxygen gas, going to make steam, water gas, all right? So, I want to balance the equation. It bothers me when they're not balanced. All right, so, in chemical changes, when something is burning. Being flammable means it will burn. Actually burning is the chemical change. So if you char the kosher marshmallows at the, cookout, you char all the sugar, that is a chemical change. Its ability to be burned, all right, is its chemical property, okay? If I put sodium metal in water, okay, they react violently with each other. We can have a chemical change, but the reason, the fact that they react violently are chemical properties, okay? Cool beans. All right, page 3. All right, so here, I think I might even change some of these around, but still the same principles apply. So, ionic and covalent. If we have an ionic, what we're looking for, the key here is a metal to a non-metal, okay? If we have a metal and a non-metal, that's going to be ionic, okay? On the flip side, if we have two non-metals, all right, that is going to be covalent. So, here we have nitrogen and oxygen, two nonmetals, covalent. Sodium is a metal, chlorine is not, ionic. Sulfur, nonmetal, oxygen, nonmetal, covalent. Cesium, sulfur. Cesium's a metal, makes it ionic. Nitrogen and hydrogen, both nonmetals, covalent. I think we have a typo here. Oh, Mg, there it is. Sorry, I couldn't see it. Magnesium iodide. So magnesium is a metal, iodide is nonmetal, ionic. Hydrogen nonmetal, oxygen nonmetal, you get covalent. Magnesium nitride. Okay, magnesium is a metal, this polyatomic is a nonmetal, so we end up with an ionic bond. All right, so really what you're looking for is if you have two metals, you get a covalent bond. If you have a one metal and a non-metal, you get an ionic bond. Let's go and erase this. So once again, for our purposes, we cut this out. COVID claimed it. Okay. Also, we cut out naming compounds. So just ran out of time. All right, so yep, don't worry about those. I'm going to so what we're going to do now is I'm going to switch back over to PowerPoint. I'm going to switch back over to PowerPoint. Going to work through these 10 reactions. Now, we didn't do types of reactions, like we just X'd out all that. So when you're doing yours, don't worry about this portion, okay? We're just worried about what we got for the actual balanced equations.